longitudinal direction also not, because you see in the primary zone here, the temperature will be much higher than the TIT. And this is gradually reduced by the addition of air that is coming from the side here and coming like this in the combustion chamber. So a combustion chamber is very complex from a temperature point of view. You start with a very high temperature, decreasing, and you have also in the radial direction a temperature profile that is extremely complex in order to protect the blade that you have behind, protect the rotating blade or the non-rotating blade also that you have behind. And you see that these two new parameters are really changing the explanations we gave until now, because in fact the combustion chamber is much more complex than what we have explained until today. And of course, the two other parameters that we have here are, let's say, much better known compared to what we have explained before. And eta Cc, that we will discuss also later on, again, when we will have discussed the injectors, is really something that can be influenced by a lot of parameters, because eta Cc, this is related to the completeness of the combustion. So you can define lambda Cc in different ways. You can define lambda Cc in such a way. You can say this is the TT3 that you are obtaining, the obtained one, compared with the TT3, let's say theoretical, that you would have used, that you would have get, sorry, with a constant m dot f. So you have a certain m dot f that is injected at the entrance of the combustion chamber. You measure the TT3. Of course, you see that the TT3 that you are measuring is everything except the TT3 average. So you need to define what is this TT3 average that you have there. This TT3 average is the sum of m dot I TTTI. If you have, I don't know, 7 thermocoppers measuring TTI, each of them is seeing or is related with a certain mass flow rate, and you divide that by the sum of the mass flow rate, and you obtain this TT3. And you can compare this with the value that you compute. So this is the computed value that you would obtain with, let's say, a complete combustion. And the ratio, this one will be lower than this one. The ratio can be a definition of eta Cc. Okay? You could also define eta Cc in another way. You could also define eta Cc in another way, but that is much more theoretical because here we understand and we inject a certain amount of fuel, we measure the TTI at different places, and you compute the TT3 and you compare the average value with the theoretical or computed one. Eta Cc could also be defined for a certain TIT that is, let's say, fixed. A certain TIT that is fixed. And you could compute the m dot f that is needed to reach this TIT, and you could inject a certain amount so that you reach this TIT. And this amount will be larger than this one. So the real m dot f that is injected and burned that is injected so that you reach the same TIT that is fixed for the computation of the m dot f that you have in the theoretical case. So this is much more theoretical than this one that you can do in a real combustion chamber. The problem with eta CC is that eta CC is depending on a lot of parameters. I have indicated them there. The speed of the flow, let's call it V2. It can be maybe V2 in the section A prime, A2 prime, we can discuss. It's also PT2, it's also TT2, and it's also, let's say, the fuel to air ratio that you have in the combustion chamber, okay? And globally speaking, you will have eta CC that will, with PT2 multiplied by TT2 divided by V2, you will have a function like this. You must be with a high PT2, you must be with a high TT2, you must be with a small V2. V2, this is more the speed at the entrance of the combustion chamber than V2 maybe. And you can reach like this values like 99.9%. This is quite possible. Of course, you need also to have the right fuel to air ratio. And here, so the fuel to air ratio that you must have must be also rather high. Whereas in these conditions, very often you will have so lower fuel to air ratio, and here large fuel to air ratio. So this is the combinations of parameters that you need to have. There is another way, so here we have mainly represented that compared to these parameters. There is another way to represent the situation. This is to represent eta CC in function of the fuel to air ratio. So the amount of air that you have into the system. Sorry, it's not the fuel to air ratio that I'm representing here. This is 1 divided by the fuel to air ratio. So the amount of air divided by the amount of fuel. And you will have a curve that is like this. So, and this is in this region that we need to work with a high fuel to air ratio. And this is very important to notify because you can do the same when you are in fact at high altitude. When you are at high altitude, this one is at low altitude. And you can go even to very high altitude maybe, to very high altitude for business jets, for example, that are sometimes flying at 15 kilometers instead of 10 or 11. It will also decrease. Why? Because altitude, note that, very important, altitude is very negatively influencing the PT2. For a given pressure ratio, the PT2 is decreased by 60, 70, 80%. So because the pressure altitude is decreasing so much, is decreasing by 80% between sea level and 36,000 feet. And so you have a very negative effect of altitude. And maybe that you can reach 99.9% at sea level. This is something that you can reach at sea level, but maybe that when you are going to 36,000 feet, maybe you have only 98% or 98.5, something like that. And when you are even going to higher altitude and worse conditions of the fuel to air ratio, maybe you are going to 96 or something like that. So you must be extremely careful when you are doing computations with this parameter eta CC. Go and look to references if you have a doubt, because the altitude will have a very negative effect. And don't forget, in the afterburning combustion chamber, where you have a much higher speed and no pipe, you have a big hole. And there you can have an eta CC that is lower than 90%, lower than 90%, especially when you have a high bypass ratio, because this is decreasing the TT2, and eta CC can go down to 85% or something like this. in the afterburning combustion chamber. So be very, very careful with eta Cc. It can go from a value that we always note 99.9% down to 99, 98 in cruise, maybe lower if you are cruising at very high altitude, and much lower in the afterburning combustion chamber. So be very, very careful, and that will also have a large influence at the level of the emissions, of course, at the level of the emissions, because that means that you will have unburned fuel that is leaving the engine if you are at a very high altitude, and especially if you have a very cold weather in the winter, for example, where the temperature can be even 10, 15, 20 degrees lower than in the summer at these altitudes. Okay? So, very important, this eta Cc, it's not exactly what we have said before, because we have never really discussed this eta Cc, the values that you could have in the cycles, in the analysis of the cycles. And then you have the lambda Cc. The lambda Cc, this is a difficult animal. So I come back to the definition of lambda Cc that I gave a few minutes ago. And this lambda Cc will be, in fact, a factor that can change really a lot depending on the type of combustion chamber you will have. And you will make an exercise on that, on the pressure losses, the total pressure losses that you have in a combustion chamber. So, what is the problem? In fact, there are two phenomena taking place in parallel. A first problem will be the friction. So you will have friction of the air or of the gases against the walls. So you see that there is an external wall, there is an internal wall on one side, on two sides, so you have three sides where you have friction, 1, 2, 3. You have also an injector, maybe, where you will have also some friction. And so you will have what is called the cold friction losses. The cold friction losses that are related with friction of the air or the exhaust gases on the walls. And we know that the friction losses are proportional with the Mach or speed square. Okay? Of course, you have decreased the speed, this is good, but afterwards you see that you increase the speed again, and if you increase the speed from 40 to 100, 150, let's say 100 is 2.5 times more square. This is giving you an increase with a factor 5 in the pressure losses that you have due to friction only. And this is frictioning, again, one side, two sides, three sides, plus some external walls that you have.